maybe DC or AC. If there is a load, maybe AC or DC, then we need to have a power conversion process. And we have seen basically four type of power electron converters which are being used for this purpose, right? Now, then we have seen that if we want to convert a given fixed DC voltage to a variable DC voltage, then what are the different methods? Voltage divider circuit, then we went for linear mode power supplies, then we went for switch mode power supply. Then we have seen various advantages of the switch mode power supplies. Then we also have seen that the switch mode power supply may, or DC to DC converter in general, will have various topologies, and these topologies, depending upon the applications, will have different advantages. Now, then we have seen various applications of these power electronic converters in laptop power supply system, in DC microgrid, AC microgrid, hybrid vehicles, or maybe electric vehicles, and that things we have seen. Now, let us talk about the before we go for analyzing different DC to DC converter topologies, the basic units which are being used that we have seen. We need switches, we need magnetics, we need capacitors, then resistance as a load. These four components are essential. We have seen in yesterday's class. Now, let us see what is the inductor. So if we see about inductor, then inductor basically is used to store the energy for some time in a DC to DC converter, then release the energy, right? And ideal inductor, this is the ideal inductor, and if some current I is flowing through this, then there will be a voltage VL across this, and this VL will be given as L di by dt, right? VL is equal to L di by dt, and if you say I, then this will be 1 upon L VL dt. This is the inductor current at time t, and if 0 to t, right? So this is for ideal case, but if this inductor, inductor is bound of what is the inductor basically? Inductor is given and reluctance, right? And reluctance L upon UA. So all this reluctance value depends on the physical parameters. What is the length of magnetic path? What is the cross-sectional area of the magnetic path? What is the permeability of the magnetic path? Upon that, reluctance will depend. Then number of turns. How many turns are there? Based upon that, this inductance. One of our professor will take the lecture how to design this magnetics, or maybe I will take in last if time permits. So this L depending upon that. Right. So L, this number of turns means how many turns or how many times you are winding this wire across the core. Or how many times. Then depending upon this wire will have certain resistance. So every inductor will have certain resistance, and we represent this resistance in series with it. So whenever there is an inductor current flowing through this inductor, then this inductor current will pass through this inductor as well as through this resistance. So this IL will be responsible, or this IL will cause the losses in this RL, so which we call the losses acting across this inductor. So this RL is called ESR, equivalent series resistance, ESR. So this RL will be representing the entire losses which is there in the inductor. So IL square into RL will give the losses in the inductor. Now similarly, we have another component, that is the capacitor. Now this capacitor is there, and whenever there is a current through this, then there will be voltage across this. We'll take this polarity, the side on which current is entering, we will mark it as positive. Similarly, here also in inductor case also, the side of inductor through this current is entering, we will mark it positive, right? So in this case, this VC is given as 1 by C IC dt, or you can say IC is C dVc by dt. Okay, and this is 0 to T. So this is our capacitor voltage, ideal case. But if this capacitor is not ideal, then this will also have certain losses. And in order to represent those losses, we take one component of resistance, that is RC, in series with this capacitance. Now, whenever there is a current through this capacitor, and obviously we are representing this RC or maybe RL external to capacitor, but they are not external. It is just for mathematical representation, which will help us to model the DC to DC converter. These are integral part of the capacitor or the inductor, but just for representation purpose, we are just for analysis purpose, we are representing them in series with this capacitor so that they represent the losses in capacitor or maybe the inductor. So whenever this IC is passing through this capacitor, then definitely this will cause a voltage because this current will pass through this capacitor, so voltage will rise or voltage will vary. But this IC, this current is also passing through this RC, right? So there will be one voltage drop across this also. So that is VRC. Let's say represent with VRC. So what will happen? The total voltage, which is across this capacitor, physical capacitor, if you see, then this will be sum of this VC dash will be sum of BC plus VRC, right? This will be sum of VC plus VRC. And this RC is called again equivalent series resistance of capacitor. Okay, so these are the two components in non-ideal form. We will do analysis of the one of the converter, including non-ideality, and then we'll see that how things change when we incorporate the non-ideality. Sometimes they have a vital impact on the performance of the converter. So it is always better to include the non-idealities in analysis. Now, next important component comes out to be switch, which is right. So there are various switches we use. So diode is also kind of one switch, which we call to be uncontrolled switch. Then we use SCR. What is the full form of SCR? Can anyone of you type in the chat box, please? If anyone can tell what is the full form of SCR? So SCR is basically silicon controlled rectifier. And these SCRs are used in rectifier circuits only, where we convert AC to DC. They are very slow operating devices which are works on line frequency. They works on line frequency, right? And you know that we will not cover in this particular FDP these things in detail, but SCR has three terminals, right? One is anode, one is cathode, one is gate. So if apply any positive voltage across anode and cathode, that will not allow to pass the current through the switch until unless you are applying the gate current. So proper gate current is required to make the conduction, to ensure the conduction of this device, right? This device. So this is called, this is upper version of diode. We have a control over it, right? In diode, we don't have control over it. But for example, just what I want to explain over here, let's say we consider a diode. If this diode is an ideal diode, then what will happen? If I see the IV characteristics of the diode, in ideal case, as soon as I apply any positive voltage, as soon as I apply any positive voltage across this diode, this should turn on. This should turn on, and it should carry any amount of current. So ideally, this follow, right? And if I'm applying any negative voltage across this, let me take this green one. If I'm applying any negative voltage across this, any amount, let's say any amount of voltage across this, then what should happen? It should not conduct. It should not provide any current, and voltage is there. So this should be the ideal characteristics of this diode, but it does not happen so. That it does not happen so. We see that whenever we apply a positive voltage across this, whenever we apply a positive voltage across this, there is a depletion layer, right? So that depletion layer width will be reduced, and it will take some voltage, maybe 0.7 volt, maybe 1 volt. Then after that, conduction will start slowly, slowly. After that, conduction will start, and it will go like this, right? And after that, also even this 0.7 voltage, or we say to be forward voltage drop. After that, also this is not a straight line, right? It will depend upon the internal resistance of the diode, and accordingly this slope will be decided. Accordingly, this slope is being decided. Based upon that, we find that even after conduction of this diode, hmm, there is this 0.7 voltage, 0.7 volt is there. Then after this, after that also there is a resistance. Depending upon the amount of current which is being carried through this diode, so drop will be there. So in practical case, how we represent this diode when in on condition. In on condition, we represent it as an ideal diode, then 0.7 volt, then RD. So if it is a on, then obviously this is shorted. Then in practical condition, this is the terminal behavior of the diode. So this is whatever forward voltage drop BF or BD or VD we define, then this is the resistance. So ideally it should have been 0 volt, right? Whatever amount of current, but now it will be different. This VAK now will be VF plus whatever amount of current is there into RD. So this voltage, obviously this will be little only 1, 2, 3 volt only, but yeah, it is there. Similarly, when this diode is conducting in reverse direction, means whenever this voltage is there, negative voltage, ideally there should be no current flowing through it. But we know that when this diode is subjected to a negative voltage, or you can say it is reverse biased, then also as you apply the voltage, then what will happen? The very in microamperes, very less amount of uh, current will flow. Then you keep on applying negative voltage, negative voltage, negative voltage. Then ultimately, what will happen? A certain breakover voltage will be there, and it will take place. And now diode will no longer be able to right? Even if really it should, but no, because this can reverse bias is represented by once again these are off, the off resistance of the diode when it is reverse biased. So what we seen that in a non-ideal scenario, in a practical scenario, these devices have certain losses, and in order to find out the proper analysis, efficiency, performance, we should know that what is the difference between ideal devices and what is the difference between non-ideal devices, right? So, okay, so we are talking, when we are talking about devices, let me introduce few more devices. So, one is SCR, which we normally use in rectifier circuits. Now, the other is BJT, bipolar junction transistor. So, these BJT are low frequency devices, and normally they are used in linear mode. Normally, they are mostly used for amplifier purpose, linear mode or active region, and they are controlled using base current. By controlling base current, we can control their gain, etc. Right, and mostly useful for moderate power level or low power level. But the another devices which we use in our converters or inverters, one is IGBT. So what is the full form of IGBT? Insulated gate bipolar transistor. So when we talk about frequency, the frequency is moderate, higher than the higher than BJT, and they can be used for high power applications. High power applications. Their frequency is, better than BJT. Another which is MOSFET, which metal oxide metal oxide transistor. So that then we have various advantages. The circuit becomes complex, and other advantages I have already uh, told you. But the power handling capacity, that is medium. So this frequency is better than MOSFET, but this power handling capacity is lower than IGBT. Okay, and both are IGBT and MOSFET, both are voltage control devices. Both are voltage control devices. By controlling the voltage, uh, so okay, if you go to the symbols, then this IGBT has, so first let us talk about BJT. This BJT has this symbol. There is base terminal, base, then one is collector, which is C, then this is emitter. So, emitter, that is E. Okay. This is three-terminal device where this base is used as a control terminal. By controlling the base current IB, we can control the characteristics of this BJT. IGBT, if we talk about, then IGBT has this kind of symbol. We have a gate terminal, then have, then we have collector, right? And now we are controlling this gate voltage. We can control this on and off period of device. and accordingly the voltage or current may be controlled in the circuit where the switch is used. If we talk about MOSFET, then MOSFET is in MOSFET we have one gate terminal, we have one gate, one drain terminal, drain, and one is source, source terminal. Okay, so this way it takes the current, and by controlling the voltage, voice is not clear. Just check voice is clear or not, please. By controlling the gate to source voltage, we can control the on and off time of this device, and then the further impact on the circuit function. So that is the way we can use these MOSFETs. So normally MOSFETs are silicon controlled. So far it was being used. Nowadays this wide band gap WBG devices are being used. So you must have heard silicon carbide and gallium nitride devices. So these devices can withstand with the large thermal, large temperature, large voltage, large temperature handling capability they have. So one speaker will talk about these in more detail. So these devices are in popularity. Okay. Okay. Now let us go to the comparison and what is the feature of these ideal devices. Ideal switch versus non-ideal switch. So first we talk about characteristics of ideal switch. First we talk about characteristics of an ideal switch. You must be able to see one waveform over here. Now, let's say this is a device. I'm representing it is with generalized symbol. It may be any device, MOSFET, IGBT, maybe SCR, maybe diode, whatsoever, right? So this is a device. Let's say it is carrying current in this direction, and this is the voltage across this, and maybe some control terminal is there. We are not worrying about. So whenever it's connected in the circuit, and let's say it is on. So when it is on, it means the voltage across this device should be ideally zero. So this is the voltage across the device, the voltage current, right? And this is, let's say it's A terminal, it's a B terminal, A terminal, it's a B terminal. If it is ideal, then what we expect when this is on? When this is on, this V should be zero, and this I, that should be whatever I want. It may be 20 ampere, 1000 ampere, 10,000, 1 mega ampere. It should be able to handle any kind of voltage. Similarly, if it is off, then this is just off. This is A terminal, this is B terminal. So this I, whatever it is, that should be zero. And the voltage which is being applied across this, right? So we are just considering this is a control device. So in control device, until unless there is a gate pulse or gate signal, whatever voltage you apply is whatever limited voltage as per the rating of the device you apply, then it will not start, right? So similarly, if this is the case, then device is off, no control signal is applied, it will not conduct, so current through this will be zero. But what we do expect that the voltage across this device, whatever voltage we apply across this, 10 volt, 20 volt, 200 volt, 2000 volt, 20 kilovolt, 2 megavolt, it should not conduct, right? That we apply, that we consider that this V should be infinite. Also, what we think, when this is on, then there should not be any resistance. When switch is on, there should not be any resistance across this, or there should not be any draw across the switch, right? So this R on resistance, that should be 0. It means the losses, which is I into R on, that should be 0. Similarly, when this is off, then what should be the ideally resistance? Can you put, what do you expect for ideal device? What should be its resistance? Can you put in chat box, please, your answers? What ideal resistance you expect? Infinite, yes, very nice. So yeah, we expect that the resistance when this device is off, that should be infinite, obviously infinite. So there will be no current through it. This is our expectation. Another expectation is that whatever switching voltage, another expectation is that whenever I want, at whatever frequency I want, echo gating. Okay. Okay, it may be due to network problem. Okay, so another expectation is that whenever I want, at whatever switching frequency, maybe 1 kilohertz, 2 kilohertz, 10 kilohertz, 100 kilohertz, 1 megahertz, this device should work. That is our expectation, that this device should function at whatever frequency I want, which may be infinite also. Because ideal means ideal person. When we say ideal person, then it should, it should be able to fulfill the all expectations. That's what we consider an ideal person or ideal switch, let's say. So in this case, all those things are being considered. Now let us summarize the things. So just I will just I type it to save the time. Just just a minute. Okay, so these are the characteristics. I hope this is visible too. These are the characteristics of an ideal switch. So what we discussed, just we have summarized. No limit on the amount of current, known as forward or reverse current, that the device can carry when in the conduction state, on state. So whenever it is in on state, it should carry any amount of current. That is the first expectation, right? Then no limit on the amount of device voltage, known as forward voltage or reverse voltage, when the device is in non-conducting state. So that's what I said. Whenever it is in off mode, then it should be able to withstand any amount of voltage. That is another expectation. Zero on state voltage drop when in the conduction state. So just what we talked, because we expect that this resistance to be zero when in on state, then this voltage drop across this should be 0. So 0 on state voltage drop, it means this R on should be 0. Infinite on of resistance, either 0 leakage current when conduction state. And last one, no limit states, 0. It means in non-conducting. And the last one, complete in zero right time, it should be a So voltage V off across this. At this instant, I said that switch should be on. So when switch was at this instant, switch was asked to be off. At this instant, switch off. At this instant, switch is asked to be on. Now switch is on. So ideally, voltage is zero, and now current has rise. That is happening, I think, due to network connection, maybe your side. So sometime whenever network connection is not good, then it combines that 10-second frame and it delivers in 5 seconds. So this becomes fast. Okay, so I think few people are facing this. So this is network issue from your side, probably. Maybe it will be better with some time, or you can connect with better internet. Fine. So whenever the switch is on, then we say that this voltage becomes zero and it will carry whatever current is required. And what we are expecting that this should not take any time. As I said to internet, it should have, as soon as I clicked on some site, it should within 0 second it should turn on, right? But it does not happen. Internet, uh, for some time it will roll, and maybe in 5 seconds that site will open. If we, whenever I say 1 GB file is there, I just click. I expect within 1 second it should be downloaded. But definitely, depending upon the speed of internet, it will take 10 seconds, 20 seconds, maybe 1 minute. And if you go 10 years back, then even you are not able to open the site, right? So with time it is happening. Similarly here also, what we expect, as soon as we give a command that switch be on, so instantly switch should be on and it should carry whatever current is there. It should not be like that, okay, it is taking some time and slowly it is going to the desired current level. No, ideal switch means at present moment only. Okay, so similarly we on at this moment, again you said should be off. Now switch is off, is there, that will be applied across the switch, and switch should be able to switch immediately. So it stop the current. That is ideal characteristics. Now if we saw the we see the power loss across the switch, power loss in switch. So because we know that power loss P is into I, so voltage across the switch into current. So when switch is on in this period, switch is off in this period. So when switch is off, only voltage is there, no current. So this power will be zero only. In this period, switch is on. So only switch is on. So when switch is on, voltage is zero, only current is available. So again, the product will be zero itself. So this period also losses will be zero. Now here loss is zero, here loss is zero. So in ideal switch, power loss is zero. That is expected from ideal switch. Now let's go to the non-ideal switch characteristics. We'll come to this later. Bad sound quality, random frequent voice. Oh, where it is coming. Here, can you please rejoin again? Is it so? Let me come to your comments first. Just a minute, let me resolve what is the issue again. हाँ सही आवाज आ रही है कितने से पूछो वहां पर कैसा डिलीवर हो रहा है ask them to reply class is being disturbed
बोल रहे हैं कि तो वगैरह में कुछ क्या है तो चैट करो देखो तुम्हारा जिंदगी क्या लिखा होगा जैसा वो बोल रहे कि डिजाइन करो वगैरह
So, do all people facing problem or few of them, please? Am I audible properly to all? Please say if I'm properly or to all. Please.
तो सबको ही आ जाएगा प्रॉब्लम
Okay, sometime jerk are there. Okay, so I think that's fine. Let me start. Let me go to back. So board is visible now. See, visible non-ideal switch. Okay, fine. So now let us come to the non-ideal switch. So non-ideal switch has lot many limitations. So we have checked with other participants. So voice is, I think, clear to them. So please, I request you, those who are not able to, you audio not clear, buffering issue. Maybe now it's clear. Okay, so I have used now this earphone. So maybe it is better. Okay, so let us come to now non-ideal switch. Okay, so in non-ideal switch, what happens? This is somewhat different from the ideal switch, and non-ideal switch is actually the practical switch we do use in hardware, or maybe we do use in simulation for exact analysis purpose. You know, and that we will see in modeling and control and maybe analysis also, that how does these things impact. So in non-ideal, if we go for this characteristic, try to understand these characteristics, then we will see that at this moment, we have switch was having certain voltage, and this is current through this certain current. So let's say this is current again, ISW. This is the voltage across the switch. So whenever switch is off, that time what will happen? There will be certain voltage across the switch. There will be certain voltage across the switch. We represent it to be V off. So let's say switch is off. First case, switch is off. So when switch is off, then VSW will be have some finite voltage. Now switch is off, so it is expected that the current should be 0 in that case. So I current, that should be switch current, that should be 0, but it does not happen so, because we have seen in case of diode also, even switch is off, there will be certain leakage current, though it is very close to 0 in milliamperes, but we cannot say that it is 0. So that leakage current will be 0, and it is given by I off. Leakage current is given by I off. Now when at this moment, let's say it's a MOSFET. So we turn on the switch. So as soon as we turn on the switch, now when switch is turned on, then what is the expected voltage across this? It should be 0. What is the expected current across this? This whatever finite current is required, right? So previously what was happening? It was instantly going to that value. But in practical case, it will not have. This voltage across the switch is there. So this will take some time to come to 0, and it will not become 0. It will be settled to some value V on, and this V on will depend upon the losses in the circuit, resistance of the circuit. So this V on will be there, and also it will take certain time T on to turn on the switch. So this T on is the time in which this voltage is settled to near to zero, in non-ideal case to some voltage V on, and it will settle to the current I on, which is some finite current, final steady state finite current. So this will be there, right? Now this is there. Now after that, this will be on whatever time we want. Now time we want. And we asked to become off. Now there is voltage, or we say to be forward voltage drop. V on what drop forward voltage drop. Now and current is there. When we say we instructed switch to be off, then what will happen? It will take certain time. The current will take certain time to drop to zero, but on ideal switch it will not be zero. It will reach to this current I off. Now it will tell you it will take certain time. So this time we call it to be turn off time. Right? Turn off time by the switch to completely off the switch, right? So after that, what will happen? At this moment it is off. Now this will remain off, and we come back here, this will remain off, and at certain time again we will instruct it to be on. Then it will take certain time, this switch voltage will go to nearly zero, which is V on. Then this current will settle to I on, and same way it will repeat, right? So what we have seen here, that voltage is not zero when switch is on, current is not zero when switch is off, the turn on and turn off time, they are not zero. A practical switch has certain turn on and turn off time. Now what about the power? So here this is V off. Earlier in ideal case this was zero, so ultimately we were having zero losses, but now V off is there. This I off is also there, though it is very small, but it is there. So this V off multiplied by I off, this will make this losses V off multiplied by I off. This will have this, and this is called conduction loss during turn on. This V off into I off, they are conduction loss during switch off, right? Now after that, what is happening? From here to here, this is a transition taking place from off to on, off to on. This time voltage is present, this time current is present. V on, yeah, what is the V on? So V on is the voltage across the switch when this is off due to certain resistances, right? V V on is the V on is the voltage drop across the switch when this is on, right? So when I'm talking about this, then this I said during off period. This is during off period. So this is V off into I off. This is a conduction loss. After that, from this period, when switch is moving off to on, this is transition period, and this is transition period current. So multiplication of this, because this is a linear, or you can say non-linear current, and this is also, so it will have this kind of shape, and this is called the switching loss. This period is switching loss when switch is trying to get on. After that, once it is settled back here, then now in this period switch is on, so there will be V on voltage and I on current. So both will constitute this I on into V on, this conduction losses. So V on into I on. This product of this is the conduction loss. This is the conduction loss during switch on, during switch on. So whatever period it is on, it will be there. Now when this comes that we need to off the switch, then what will happen? This current will reduce to zero, and this current will increase. Now when this current is reduced and this voltage is increasing, so during this period During this period, what will happen? Both voltage and currents are there. So again, this period will be there. Sorry, this power loss will be there. So this is the power loss. This is the power loss corresponding to transients, switching transients during turn off. So this loss will be there, and after that again, once it is settled down, and this. So what we see here, losses are there when of losses. One is conduction loss, which is during this V of I of, and this V on I on, and another is switching losses. No, it will be different depending upon the value of V of I of and V on I on, right? So this period is related to transient switching loss during on period. This is switching loss during off period. Now depending upon T on and T off, these losses may be different, right? So let's summarize the things. For a non-ideal switch, okay, so let us summarize the characteristics. So limited power handling capability, that is limited conduction current when switch is on, and limited blocking capability when switch is off. So that is obvious. In which conduction current and limited whatever voltage capacity. So any device can carry any amount of current, any device can block any amount of voltage. A practical device, yes, it depends upon the. If you are having switch current very, so we have taken small, so we have taken if it is there. If value of I is 0, then obviously that will not be there. That's correct only, but again it depends upon the switch to switch. So we have considering it. We are considering, okay. So limited power handling capability. Okay, so we have certain rating, voltage and current ratings, and also the, because this turn on time and turn off time, they are coming into picture. That's why they are blocking our on period and off period. So ultimately they limit on the frequency. So we cannot have infinite frequency, limited switching speed or limited frequency, that is caused by the finite turn on and turn off times. Okay, then finite on state and off state resistances, yes, obviously, due to which only this leakage current and voltage drop is happening, so that is there. And because of the characteristic above, the practical switch experience power losses in on and off states known as conduction losses, and during switching transitions known as switching losses. So that we have seen, if these things are absent, it is immediately on or immediately off, then switching losses will not be there. Infinite switching frequency, turn on time is 0, turn off time is there 0, then it will not be there. So how to do analysis of these things, these losses? So I'll because time is running so fast, I will just brief it. How to go for a new page? धीरे, ये कैसे हटेगा देखना, ये क्या प्रॉब्लम आ गया? ये वाला हटाओ, मुझे नया पेज इंक्लूड करना है। I have kept unmute, please wait for 30 seconds. Okay, new page added. Okay, so now how to do analysis for such circuits? So just well, so basically this is our original circuit, and we have seen that here this vary in non-linear fashion. This current and voltages, they are varying in non-linear fashion, but for analysis purpose, what we can do, we can consider it to be linear equation, right? Similarly, this to be a linear equation like this. So when this is moving that way, then we can write the, see, when in this duration we can simply write the equations for this voltage and current, but during this and this we cannot write, but if we linearize it, then we can write these equations correctly. And similarly during this off period also we can write the equations. Now if we are analyzing this, then let me tell you. So if we want to find the loss across this switch, average loss across this switch, so that will be 1 upon T, 0 to T, IHW, VHW, dt. So this will give me the entire losses across the switch, including conduction losses plus the switching losses. So it will give including conduction losses plus average switching losses, right? So when I talk about the switching losses, P switching, then it will be 1 upon T, where T is the total time period from for one cycle, right? This is the total time period from here to here. Then this will be just from, sorry, 0 to T on. If you see, it is from 0 to T on, 0 to T on, and during that period, 0 to T on, during that period, what is the current equation, what is the voltage equation, that we need to know. So IHW, VHW, dt. Plus, if I take this as a waveform, then during this period T off, during this period T off, what is the losses? So if I say it to be 0 to T off, then this ISW, DHW during this new time reference, that will give me the switching losses. And similarly, if I want to find the conduction losses, so conduction losses are a bit easy to find, so that is 1 upon T. Now this time period for which, if I talk about this T, let's say this T total, then switching losses are for this period only, right? So depending upon how you consider, like turn on time, turn off time, you consider for part of dt, or maybe 1 minus dt, how do you consider, depending upon these losses will vary. Like if you take this figure, then here this turn on loss, this turn on transient loss, and turn off transient loss, both are considered as a part of dt, right? And the only this 1 minus dt, this off losses are considered here. So depending upon that, we will analysis the waveforms. So this 1 upon T, and whatever is your conduction losses for on time plus conduction losses during off time, that you will take and take the average of that. So this will give you conduction loss and switching loss. and that will finally we will get the total losses. So if you simplify this circuit and if I write the final equation, you can simplify, then this losses comes out to be V of I on upon Ts, T on plus T off upon 6 plus V on I on upon Ts minus T on minus T off. So certainly we have taken assumptions, like some of you messaged me in chat box also. So here I off, which is normally 0, leakage current is normally 0, so that we have also considered uh, 0 in this derivation. So what we see here, that this is conduction loss. This is conduction loss and this is switching loss. This is switching loss. So switching loss is dependent upon V of ion and switching periods T on T off, right? Switching periods T on T off and Ts. So 1 upon Ts is what? Switching frequency, na? Switching frequency 1 upon Ts. So from here, if we see, the switching loss is directly proportional to frequency. Switching losses are directly proportional to switching frequency. So more the switching frequency, more will be the losses. More will be the losses. But if our switches are such that they are having less T on and less T off, less T on and less T off, then the switching losses can be minimized, can be mitigated, can be lowered, right? And this conduction loss will depend basically on V on and I on, V on and I on, and they are almost independent of the switching frequency. Why? You can see a Ts minus T on T off upon Ts. So if T on and T off is very less in comparison to Ts, so this is Ts itself, so Ts divided by Ts, so that will cancel out. So this conduction loss will practically not depend upon the switching frequency, that they will depend upon the voltage and currents only, V on I on only. So this is how we have to take care of the switching losses. If we sometime in some research papers we have seen that they carry out all calculations of switching losses and conduction losses to analyze the efficiency of the converter. So this will help in that way. It is given in one textbook, Isa Watterse. If you want to do it more, then I suggest one book over here, Power Electronic Circuits by Isa Batterse. So this book, there is one chapter in that this whole analysis is given, or and maybe in another books also it is given. I have followed from that, so you can refer if you want to go into this more. Okay, so now let us. So this is what we have talked about the switches. Now let us go to the analysis of converter. So analysis of converters, DC to DC converters. So before going to analyze any DC to DC converter, uh, we see it operates in two modes. One we call to be CCM, continuous current conduction mode, and another is DCM. We will try to discuss both the cases. DCM, discontinuous current conduction mode. So whenever we talk about a DC to DC converter, certainly it will have at least one capacitor and at least one inductor. So when we talk about inductor current and especially in steady state. So if this inductor current is always greater than 0, always greater than 0, then we call it to be continuous current conduction mode, right? And if it is not always 0, for some time, at least for one switching period, for some time, so this is case of continuous current conduction mode. But if it happens so that this is kind of this waveform, if this is time period t, this is its on period, which is d into t, and this is its off period 1 minus dt. And similarly I write here, so this is dt, this is 1 minus dt. Okay, so during this entire period t, current is never falling to 0, but here during this period t, the current is rising, it is reaching here, this is becoming 0 before the start of new cycle. So this falls to 0 for certain time during one switching period, then we call it to be DCM mode. So we will do analysis, we will assume when doing analysis that this is CCM mode, this is DCM mode. When CCM mode occurs, when DCM mode occurs, that we will discuss. So what is the advantage and disadvantage of the CCM DCM? So as I said, the definition, inductor current never falls to 0 during the switching cycle. So what happens when CCM is there, then it has lower peak currents because current is continuous, so it will not reach to higher peaks. Better efficiency for medium to low loads, it will have better efficiency, right? And because inductor current is continuous, due to which the output voltage ripple, we'll see later in analysis, output voltage ripple which is appearing across the capacitor. So this inductor itself is controlling the ripples, therefore the load on the capacitor will be less and the output voltage which is appearing across this capacitor, that will be less output voltage ripples, right? And when it is continuous current conduction, then it's easier to design a control system. It is easier to design a control system. We can do the mathematical modeling very easily. And similarly, because this is inductor current is continuous, so this di by dt is low, due to which this EMI, electromagnetic interference, that will be lesser. But what is the requirement for getting some advantage? We have to pay something. So in order to keep the current continuous, we have to use a large size inductor. How to design this inductor, that we are going to talk in this lecture itself. Now, because the inductance is there, so inductance, that uh, that makes the system sluggish. So slower transient response, increase switching losses because switch will be on and off for more time, so it increases the switching losses. Then it is not suitable for low power applications due to its light loads. At light loads, CCM is not better. At light loads, DCM is better. DCM is having better efficiency. Okay, in comparison to DCM, has its own uh, whatever is here will be reverse of it. In DCM, you end up smaller size test. Right? That is performing better on light loads. Light loads. If load is because So in DCM, peaks are high, DI/dt will be high. Therefore, this EMI interference will be more in case of DCM. So this is basically comparison between DCM and CCM. Inductor current, if we talk about, it never falls to zero. In this, it falls to zero. Inductor size obviously larger here in CCM, smaller in DCM. Peak current will be low in CCM. In DCM, it is high. Efficiency at light load, as I said earlier, it is lower here in CCM but higher in DCM. Output voltage ripple, because inductor is taking care of, so it will be lower in the CCM, higher in the DCM. Control complexity, because number of mode increases in the DCM due to the zero inductor current, so it is more complex in DCM, and this mathematical modeling also easier in CCM itself. Due to low DI/dt, lower EMI in case of CCM, more EMI in case of DCM. And load condition, for medium to high load we use CCM, but light load we use the DCM. So this is the two modes which we normally use. Now let us do analysis of very first converter, which is buck converter. So let us draw the circuit diagram. I know why we use DCM at light loads. That, madam, you will come to know in the lecture itself. Yeah, why we use, because it's preferable. I'll tell you maybe in analysis of this buck converter itself, it will be understood. Okay, so for this is buck converter is just an example, but we can generalize the analysis to other converter as well. So we'll try to understand this operating principle well. Okay, so okay. So if I take this ready-made figures, you will be able. Okay, well, so let us take, this is VG, it will be easier. So we consider first the inductor current direction, and accordingly the inductor voltage we consider. Then we consider the capacitor current direction and capacitor voltage accordingly, and the load voltage and load current directions as well. Right now we are going to steady state analysis. I think most of you have already learned. Now we will see how this converter behaves in transient mode. Again, we can do analysis in transient mode and steady state mode. So we will first see its operation in transient mode. Okay, so just again, once again, I will draw one figure here. Yes. So we are doing its analysis first in transient mode, then we'll go to the steady state mode. But before that, we assume certain things. So assumptions. So first assumptions, we are considering that all the inductors, switches, diodes, components are ideal. All the components are ideal, right? And second is that this converter is operating in CCM. Third is the switching frequency F and duty cycle is D. Now when this converter is in first mode, switch on mode, so mode 1, that is switch on. So for 0 to dt period, this converter is on. So let's say very first cycle, we are not considering steady state. So initially the capacitor voltage is 0, inductor current is 0, very first cycle. Now we have just turned on the switch, switch. So the G is being applied across this diode. This is minus, this is minus, this is plus. Okay, so this becomes reverse bias. So this diode will be off, switch is on now. This will be the equivalent circuit. Now, in analysis of any converter, we need two things. One is the inductor voltage, another is the capacitor current. The number of inductors, number of capacitors. For all capacitors and for all inductors, we need to know these things: inductor voltage and capacitor current. So let's say inductor voltage. If I say inductor voltage in this mode, so inductor voltage VL is now this input voltage minus this capacitor voltage VC, which is now same as VT. So this is minus VT, right? Now one phenomena which we use in this analysis, that is small ripple approximation. Small ripple approximation, or we say to be SRA. So what is the SRA? In SRA means like let's say this is the your output voltage. So what we do consider that this whatever small ripples are there, they are neglected, and we consider its value to be fixed V naught. That's also in assumptions. Also we consider that the value here, fourth assumption you may write that value of capacitors is sufficiently large so that this output voltage can be assumed constant, so that output voltage can be assumed nearly be assumed constant. Okay, so if we use this SRA, this VL can be written as Vg minus V naught. Okay, now at starting particular moment, so this VL is what? LdI by dt, LdI by dt. So di by dt, that is Vg minus V naught upon L, right? Very first cycle here, we consider here, right? At very first cycle, V naught is 0. So what is di by dt? 0. So V naught is G upon L only. So now increase slope, inductor current will increase with this slope. So here, this inductor current is increasing with this slope Vg upon L, and it will reach to certain value. It will reach to certain value. Now when mode 2 is there, if mode 2, I talk about mode 2. So in mode 2, what is the equation? What happens mode 2? This switch is off. Now this switch is off, and this current which is there in the inductor at this point, this current, now that current was coming from this source. Now this current need to find a path, so it will go like this way, and this make the diode turn on. This make the diode turn on. Now this diode will turn on, so this will be the equivalent circuit. Now when this is the equivalent circuit, then what is the VLT? Now in this case, VLT is minus of V naught after SRA, small ripple approximation. Now this is the VLT, and so this is basically di by dt, that is minus V naught upon L, right? But what is the value of capacitor voltage? The capacitor voltage value is 0. So in very first step, this will be almost 0. Now if it is 0, it means slope will become 0. So whatever current is there, that current will be there. So this current will continue. So this inductor current now, or you can say the energy which was stored over here, now this will flow through this capacitor and load. So capacitor will be somewhat charged. This capacitor will be somewhat charged now. So in this case, the value of V naught will be increased somewhat, right? So we'll come to this point. Now at t equal to Ts, what will happen? Again, this is on. If this is on, this will be the equivalent circuit. If this is the equivalent circuit, then this equation will work. Now this equation di by dt equal to Vg minus V naught upon L. Now V naught has some value. V naught has some value. Vg is fixed, L is fixed. So Vg minus V naught upon L. So now this slope has little bit decreased. This slope has little bit decreased. Now this slope has decreased, right? Now in this case, what is happening? This inductor is again storing the energy. This inductor is again storing the energy. At this moment, again this switch is made off. So this circuit will work. Now if this circuit is working, then what is happening? This inductor has stored the energy. Now this energy will be released to this, right? This energy will be released to this. But previously what was happening? V naught was 0. But now in second cycle, this V naught is not 0. It is having some value. So this will have certain slope, but negative. So it is not now constant. This is having some slope, right? This is having some slope, negative slope. After this, what will happen in next cycle? Again, this switch will be on. So this will be the equivalent circuit. We will follow this equation. Now the value of V naught has increased. So this slope in on condition, this slope in on condition, this slope, let me take another, this slope will further decrease. So inductor will store the energy. Now when switch is off over here, then what will happen? This circuit will be the equivalent circuit. Now this has stored the energy. So further this will charge this capacitor. So this capacitor will have more value now. So if it is having more value, then this slope will further increase, but negatively. So this slope is also increasing negatively. So this is decreasing, this is decreasing, this is increasing magnitude wise. One is positively decreasing, another is negatively increasing. So certain point will come, this cycle will go on, that both the slope, this slope and this slope, both the slope becomes equal, right? Both the slopes becomes equal and we reach to steady state. So during transient period, this will behave, and this transient period definitely will depend upon the L, because value of L is coming into picture. So that way this converter works in transient condition, and after when it reaches to equilibrium, there will be a condition when this IL at this point and at this point, that will be same. Any 2 points which is having the gap of t, the current magnitude will remain same. That way it reaches to steady state. Once it reaches to steady state, then how we do analysis? So now we are considering screen locked. Anyone else with screen is moving or not? Just check. Huh? Not moving. क्या आ रहा है इस पे लास्ट? वही happens sir. Let me resolve this issue first, please.
हाँ कंपैरिजन टेबल आता है।
So after few switching cycles, uh, this on and off slopes becomes same, and when these slopes become same, then we will say that we have reached to equilibrium. We have reached to equilibrium state. Now in steady state, how do analyze to steady state? So let slide. So we just take these figures from here. Okay. So this is on period. Switch is on in this period 0 to dt. In this period switch is off dt. So we will write the equations for inductor voltage VL. In this case, so VL is Vg minus V naught. Okay. So from here L di by dt, that comes out to be Vg minus V naught upon L. So this is the equation during turn on time. Similarly, if I want to write the equation for this capacitor current IC, so that is IL minus this current I naught. Okay, so this current is I naught, which is V naught upon R. So this is one equation, two equation, three equation. If I write the same equations for this off period, so VL is in this case minus V naught, and L di by dt, that is minus V naught upon L. And the third equation, so this is equation 4, equation 5, and IC is IL minus V naught upon R. Equation 6. So once we have written this, now we know that in A, we write these waveforms. So when switch is on, then this is Vg minus V naught. So let's say this is Vg minus V on for this material. And when switch is off, then this is this voltage. So this is inductor voltage. This is Vg minus V naught, and this is minus V naught. Similarly, if I draw the inductor current for this period in steady state, then during this on period, this is increasing, this is decreasing, and same thing gets repeated. So this period is dt, this period is 1 minus dt. Okay, so this is the inductor current. Now there is one principle which is called volt second balance, or another thing, in steady state, the average in steady state average voltage across inductor, that should be 0. This is principle for any condition for an inductor. In one switching cycle, the average voltage across the inductor should be 0. So if I take this inductor, then average of this, so what is the VL average of this? That is 1 upon L, 0 to T, not 1 upon L, 0 to T, VL of T dt. That should be 0. So if I take from this to this, so it becomes Vg minus V naught into dt plus minus V naught into 1 minus dt. So if you simplify this, 0 equal to t will cancel out, so dVg minus V naught d minus V naught, so it becomes V naught. So from here V naught equal to d into Vg. So this is the output voltage of this buck converter, and we know d is less than the 1, so it is step down, it is step down converter, right? So from here we can get the V naught. Now the same thing we can do with the volt second balance. So volt second balance is that whatever the inductor voltage Vg minus V naught and its time, second means time, so that is for dt period. Similarly, what is the voltage uh, across this inductor? So let us take its magnitude, so that is the V naught, or you can say plus minus V naught into 1 minus dt. So if you do so, you will arrive to the same conclusion. I'm going a bit fast because now I need to complete this topic. Only 20 minutes are left. So this is the volt second balance. Now what about the capacitor current? So this current, capacitor current, what is the capacitor current? This capacitor current is nothing but IC is equal to this IL minus V naught upon R. And because V naught we consider to be constant, so this IL minus I naught, that is the only capacitor current. And if you see the average inductor current, so this is the average inductor current, which is same as I naught, right? So if I draw the capacitor current equation, so what will be the capacitor current equation? This actual inductor current minus I naught, so this will be made of this like this, this, then this. So this will be capacitor current, okay, which is basically IL minus I naught. Equations are not visible on screen. Is it so? दिख रही है? हाँ, it's visible ना, यही तो लिखा अभी मैंने, हाँ. It's visible only. I've checked it. IL minus I naught. Okay, so this is the capacitor current. Now, I want to draw the, so yeah, this is the capacitor current. Now I want to draw the voltage, output voltage. So let us draw output voltage. So if you see a negative current, let's say this is your output voltage, average output voltage. Now here capacitor current is negative. What does that mean? Capacitor is being discharged. Capacitor is being discharged. Then after this time, so this what is this time? So this is middle of this dt by 2, and this time is also 1 minus dt by 2 from here to here. Okay. So what is happening? From here to here, this is a negative current flowing through the capacitor. It means capacitor current is out of the capacitor. So capacitor is being discharged. But after that, if you see, this capacitor current is increasing, right, then decreasing, but during this entire period, which is t by 2, this capacitor current is positive. It means the capacitor is being charged. So capacitor is being charged like this. Capacitor is being charged. Then during this period, capacitor is again being discharged. So the capacitor voltage will be decreasing. So this way, what we see here, that this is the V output minimum, and this is the V output maximum, and this is the V output, and this we call to be output voltage ripple delta V node, which is V node max minus V node minimum. This is called output voltage ripple. Okay, so I hope that these waveforms are you know uh, you can understand these waveforms, how this actually so this output voltage looks like this. Actually this output voltage looks like this. If time permits, I will show you in simulation also how does it happen. Now the comes, and this inductor current, this inductor current will reach from IL minimum to IL maximum. Now, as we said, CCM, continuous current conduction mode, it means if it is the CCM, then this IL minimum should always be greater than zero. If IL minimum becomes zero, then it's called boundary condition between CCM and DCM. So inductor current cannot be zero in this case. Zero in this negative. It will go to zero, then will remain zero for the same time. So to ensure the CCM continuous conduction mode, we have to uh, make sure that IL is always greater than zero, and it will happen when we design a proper capacitor. So let's uh, see how to design the inductor. So this is our inductor current, IL maximum, IL minimum. This period is dt, and this period is 1 minus dt, and total period is t. Okay. So if I want to take the average of this waveform, then either I can take, because this is a simple waveforms, I can directly take. So this is 1 by t, half of I can divide it into two periods also. So that way also I can do half of this dt plus the sum of these two, IL max plus IL minimum, right? This area, first area, then plus half of 1 minus dt into again sum of this and this. So that is IL max plus IL minimum. So if you simplify it, then this becomes half of IL max plus IL minimum. So that is IL average, right? That is the IL average. Now, but we know that another thing is that del IL. So del IL is IL max minus IL minimum. This is called inductor current ripple, ICR, inductor current ripple. And this 2IL from here, this 2IL is equal to IL max plus IL minimum. So if we simplify these two equations, then I can get the value of IL max. So IL max comes out to be this IL plus del IL by 2, and IL minimum comes out to be this minus del IL minimum comes as IL by 2. So you can see if this is IL and this total period is del IL. So this half of this is del IL by 2. So IL plus del IL by 2, that is IL max. IL minus del IL by 2, that is the IL minimum. So this is the equation minimum inductor current and maximum inductor current. But in order to ensure the CCM operation, let me write it here, CCM operation, what we should do, minimum, this is minimum, this is minimum. So it means IL minus del IL by 2, that should be 0. It means del IL should be, okay, let me write del IL by 2, that should be less than IL, or you can say del IL should be less than 2IL. So this is the worst case scenario. Now if this condition is there, then we can always have, I'm missing something. No, del IL. Yes, this condition should always be met. So if we go for boundary condition, so in boundary condition, this should be equal. So del IL is equal to 2IL. Now, how to find the value of this del IL? So if we go to previous equations, so here we had these two equations. L di by dt equal to Vg minus V naught upon L, or L di by dt equal to minus V naught upon L. We will take the question. So we can take any of these equations, right? So let us consider this equation in off condition. So that is L di by dt equal to this. So L d screen is not visible. How is it? So magnitude of this is V naught. So from here, screen is not visible. Visible, na? देखो क्या आ रहा है? Ma'am, it's visible. We have checked with this delay may be due to internet speed only, maybe 2 seconds or 3 seconds. So from here, del IL is equal to V. Del IL is equal to del. So if I describe that is equal to 2, and this IL is I naught, which is V naught upon R. So from here, this V naught will cancel out, and L becomes R 1 minus D into T upon 2. So this is the critical value of L, which is R 1 minus D upon 2F. Okay, so this is the critical value of inductance, R 1 minus D upon 2F. If I have L greater than this L critical, then I will have CCM operation. If this L is equal to L critical, then I will say I am at boundary condition. And if I have L less than L critical, then I will say I am in discontinuous current conduction mode. So what generally we do, we calculate this L critical, R 1 minus D upon 2F, frequency we choose, duty cycle we know, and this load we know. Then L critical value is there, then we generally take 5 to 10 times value of this L critical of L is equal to L critical. Then we can design this inductance. Now someone was asking that how this load helps. So from here, if we see L critical is equal to R1 minus D upon 2F. This is the equation. Let's say we have designed some inductance with this L critical value. Now we are at just verge of boundary. You have certain load resistance, you have certain duty cycle, you have fixed certain F. Now due to any reason, if your R is increased, so let's say previous value was for example 50 microhenry. This calculation gives us when R was 10 ohm, D was let's say some value 5 ohm, 0.5 let's say, and frequency was such that some frequency is fixed F such that it value comes to 50 microhenry, and you have designed this inductor, you have put into your circuit. Now circuit is working well. Due to some reason this R has increased, right? This R has increased. Let's say R becomes now 20 ohm. Now what is the L critical required? What is the L critical required is obviously should be double. It means it should be 100 microhenry considering all other parameters are constant. Okay. Now this is 100 microhenry, but in your actual circuit it is 50 microhenry only, and load resistance has increased to 20 ohm. So how this circuit will see that I need 100 microhenry, only 50 microhenry inductance is connected. So in DCM, it will go into DCM. So R has increased. We are saying load resistance has increased, but it does mean that load has decreased. So sometimes this term is also get confused. When we say load resistance has increased, it does not mean load has increased. If I say only load, then if I say load, then it is the current. So when given fixed voltage, if R has increased, load resistance has increased, it means load current has decreased, load has decreased, right? So if load has decreased, so better to work in DCM. Now converter is operating in DCM. That's why at light load, DCM is better. Okay, so that way we have now designed the L, value of inductance. Now how to design the value of capacitance? So we'll see that now. So design of capacitance, design of capacitance. So this was our circuit. This was inductor current, this was capacitor current, and this is load current. Okay. Now whatever voltage is appearing across the load, that is same as the voltage across the capacitor. Now we have just seen that this is our capacitor current, which is IL minimum minus IL. This is IL maximum minus I minimum. From here to here, this is the dt period. From here to here, this is 1 minus dt period. Okay, this is dt by 2 period, and from this to this, this is t by 2 period. Okay, now the output voltage we explained in the previous slide. So the capacitor voltage or the output voltage changed like this. It is decreased. So this this is del V naught. So this is V naught max. This is V naught minimum. Now when we design the capacitor, then we know one relation, 2 equal to CV. The charge stored, that is equal to C into B, capacitance into the voltage across the capacitor, that is there, right? Now what is the charge? Basically this is how current is defined, IC dt. So if I say what is dq, that is 1 by C I dt, sorry, not 1 by C, this is just I dt. So what is the charge stored? Charge stored is the area under the current curve, which is basically the area under the current. Okay, so if you see, if this is the positive current which is starting from this point, this is increasing then decreasing, this entire current is positive, right? This entire current is positive. So due to this current, whatever is the change in the voltage, what is the change in voltage? V minimum to V maximum del V. So I can say if due to this change there is del Q charge accumulated, C is the capacitance which is fixed, and this is the change in voltage, that is del V naught, right? So if anyhow I can find del Q, and what is the del Q? Area under the curve, area under this curve, right? So that I can easily find out. So what is the del Q? Del Q is the area of this curve. So first is, this is triangle, half into base into this height into this height, and what is this height? This total is del IL. So this height is del IL by 2. So this is del IL by 2. 1 upon 8 this becomes 1 upon 8 into del IL. This is the period. So let us put it to that is IL into T. So V naught L 1 minus D. Okay. So from here del IL was 1 minus dV upon F into L upon L into F. Let us put it here. So C becomes 1 upon 8 F 1 minus D V naught LF into del V naught. Okay. So from here, if I simplify del V naught upon V naught, that's come out to be del V naught upon V naught, that comes out to 1 minus D upon 8 L F square C. Okay, so this is the output voltage ripple. Or if you want to find, if output voltage ripple is given, you can find the value of capacitance, which is 1 minus D 8L F square del V naught upon V naught. So this is the value of capacitor. Now we know that if better the ripple means lesser the ripple, if lesser the ripple, output voltage ripple, then capacitance should be high. The more the capacitance, lesser will be the output voltage ripple. Okay, so that way we design the inductance and capacitance for the DC to DC converters, and it remains same for all the remains same for all the converters. Okay, so here because this triangle was simple configuration, that has simple configuration, I have just calculated Q in this way. Otherwise, if it is not known, then we could have gone through this way, IDT, whatever equation is there for that period, we could have written that. Okay, so I think time is over now. Now we will take the questions from your side. I'm sorry, actually, I'm going a bit slow to make up the fundamentals clear. Started this modeling, but once we understand these basic circuits, then mathematical modeling will be easier to understand. So, do you agree we should go a bit this mode only, learning mode, or we should go a bit fast? You know, with the help of slides and all those things, advanced things. We'll increase the speed. Speed is okay. Thank you. Okay, so we'll go for one, two lectures in this way. Then my intention is that whatever little or more we discuss, but it should be understood because more informations are already available. So if fundamentals are clear, then things will work more. So we stop here, and I open for discussions or any queries. Please send your queries in the chat box. I'll see and try to. Thank you. So try to understand the things. Now more interesting topic will come when we go to mathematical modeling, and we will try to simulate some of these things. What is the standard ripple during design? Yeah, it's a 1% for standard power supplies, 1%. I will show some of slides of my research also to you in next session. What we discussed just fundamental. Now I'll go for research part a little bit in next. So 1% is the ideal, 1% at certain time, 2% also. Sir, it depends upon applications also. But 1% is okay. It's okay. Maybe aerospace applications, then we have to go a bit lower also. So in those cases, we have to choose the capacitor very wisely. And how this ESR makes an impact on these ripples, that I will discuss you in next session once we discuss these basics of converters. No. Current ripple is normally 20% or to 40% will vary. If we decrease the current ripple to 1%, 2%, then our inductor will be very heavy, very heavy. So ripple in inductor is 20% is okay. So any more questions? Please share in the chat. Please. Most of some of you are facing this problem. Actually, we are confirming it with our some participants which are here with us. They are able to follow the things. Maybe this screen is having 1 second, 2 second delay, but the other things maybe sometimes this internet. Okay, so we can find the slides. Okay, so we will put once like maybe end of this week, or once this course is over, then we will put the slides in Canvas only. This recorded videos will also be available at Canvas, and also we'll ask myself also will give some better slides and better materials, and we'll ask the other speakers also to share their contents, study materials, so that if some of you want to refer them later on, then you can always access them from Canvas. Okay, any other question? Delay, those things are there. Locked from screen logged. So we stop here. Today we will meet at okay. Generally, we do not consider conduction losses in off state. I think that I answered. Nitishji has asked this question, so we answered that we have also neglected that in final derivation. Why use DCM at live loads? I have explained. And then all queries are okay. So, sir, if two inductors are present, then ripple in inductor current will be in terms of inductor current or output current. Yes, so that will be in terms of inductor current only. Ripples are, we actually I have not told this inductor current ripple. We always define one inductor ripple factor del IL upon IL, right? If there are two inductor current, then I say x1, x2. So it is always defined as a percentage of inductor current itself. But like if some inductor is connected to the load side, like this configuration, then what happens? This like inductor voltage in one switching cycle is 0. Similarly, for capacitor in steady state, the average capacitor current in one switching cycle is 0. You can see here also some portion is negative, some portion is positive, right? So average capacitor current is 0. So in this kind of thing, what happens? This is 0 average and capacitor current. So this inductor current is directly equal to load current, right? That's why we can use this term I node over here, but fundamentally it is defined as the percentage of its on current. Like if first inductor, so first inductor current, second inductor, so its ripple will be corresponding to second inductor current. But by chance, if it is happening that it is matching with some factor or with exactly in the same way, then we represent in term of load current. So it is not like standard way to represent in always load current. We have to match the what is the relation between the sometime maybe you have this relation IL equal to DI node maybe. So that time you cannot, if you are replacing this IL, then you have to write DI node. Okay, so I think it meets your answer. ROD, or you can WhatsApp me, or I'll send. You can send voice chat on WhatsApp if you have further questions. Sir, what the practical limit of current ripple and voltage ripple we take? That's what I said. Normally, voltage current, output voltage ripple, like this is buck converter, only one capacitor. So this output capacitor is same as output voltage, or the voltage across this capacitor is same as output voltage. So we take it to be 1%. But let's say your circuit is having 2-3 capacitors, like we say SEPI converter, CUC converter, Zeta converter. So there we have two capacitors. So one capacitor will be in between somewhere, that is just used as a medium to transfer the energy, capacitive transfer. But one capacitor is across the load. So the capacitor which is connected across the load, that capacitor voltage will directly affect the output voltage. So for that particular capacitor, we will take 1% or 2% output voltage ripple. But if some capacitors which are within the circuit elsewhere, and we are not taking their voltage or the voltage across those capacitors as output voltage, then we can little bit relaxed, 5% we can allow for those capacitors, like C1, C2 in capacitor current. So C2 is the output voltage, the capacitor, that is affecting the output voltage. So C2 we will have 1% ripple, but C1 we can have 5% also. Why it is so? Because the less ripple you have, more value of capacitance is required. The quality of capacitance required is more. So you will have the more cost. But if cost is not an issue, if we want everything well, then definitely we want cost, size, these are not the issue. Then we want the best things. So ripple should be 1% for both. So it depends upon the user demand. What is the demand? What is the cost? Constraints, accordingly we select. But if you say in general, then current may be 20% and the output capacitor 1%, and intermediate capacitors may have 5% output voltage ripple. I hope I gave your answer. Thank you. Sir, in capacity design, is ESR value plays a major role? Yeah, it is required to take ESR value. Definitely we need to take, and I will continue my next talk with these things only. I will tell you my research work, my PhD work, in which I have considered these things and how does it impact. So you will see the effect. That I will show with the help of PPT, because that is a long work, and if I explain on board, then I will not be able to cover everything. So we stop here. We will meet 2 o'clock. We have experts from IT Bombay, Dr. Ravi Prakash Reddy. So 2 o'clock be there. Okay, or accordingly we meet. Thank you. Maybe as he requested that he will not be available, I think 2 to 4 completely. He will take class 2 to 3 only. If so, then I will continue this thing 3 to 4. Thank you.